All right. As always, guys, if you have questions, please feel free to throw them in the chat or unmute yourself and talk to me. I haven't checked my sound yet today, but hopefully it'll work if you unmute and talk to me. Otherwise, just put it in the chat if that doesn't work. We are starting into a new chapter today. We are starting chapter 6, which is the beginning of our semester, and we will cover chapters 6, 7, and 8. We will end about 3 or I would say, I don't know, April-ish, and then review for about a month leading up to the AP exam, whenever that will be. And yeah, so just so you know. And all right, let me know if you can't hear me or anything, and we will get started here. We are talking estimating with finite sums today is our topic, and I want to start this conversation with something that is comfortable for us, and that is we can figure things out without calculus, but then making our connection to calculus with this. And so if I were to have told you that this gal Jane was traveling at 20 miles an hour, and she drives for 3 hours and asked you how far she had gone, I'm guessing most of us would be able to say, okay, well, she's driving 20 miles an hour and she drives 3 hours, that she's driven 60 miles. Okay. Now we can make that a little bit more official by saying, okay, well, we know our distance formula is rate times time. And that is our 20 miles an hour times our 3 hours. And that's where our 60 is coming from. Okay, so don't really need calculus, but this is a nice, easy way for us to ease into seeing this in calculus, the connection to what we're going to talk about today. And that is, okay, what if I were to draw a graph of this? And so on my graph, you see over here, I've got a picture of our x-axis being our units, our hours, our y-axis being our rate, our miles per hour. Well, she's driving at a constant rate. A constant rate in a picture would look like a horizontal line. Okay. And if we're just looking at what this is up until we get to 3 hours, that's a terrible picture. Let me try that again here. Until we get to 3 hours. Okay. What I see as I kind of draw that in is I'm creating a shape I know, first of all, and it's a rectangle. And if I compare something about that rectangle to what we know is she traveled 60 miles. Well, look at what we have in this rectangle. We have a base of 3, we have a height of 20, and if we were then to consider the area of that rectangle being base times height, we'd have an area of 60. And is it a coincidence that our area matches the distance traveled? And what it turns out is it is not, is that if we look at this as our velocity, the area created by that velocity curve under the area under our curve will end up being our total distance traveled. And this is a very easy one for us. Probably didn't need our calculus here, but let's go ahead and sum this up in this phrase right here, is that the area under a velocity curve will equal the total distance traveled. Very important phrase right there, and kind of our underlying theme for all of this. Area under a velocity curve equals total distance. Now, I started with a very basic example. We're going to take one step up from that very basic example and look at this. What if we change Jane's velocity? Last time I told you that it was a constant 20 miles an hour the whole time. Well, what if it's a linear function? What if Jane's velocity is v of t equals t plus 2 miles per hour? How far does she travel in 4 hours? Well, if I were to graph her velocity, so let's make this connection here. V of t equals t plus 2, y equals x plus 2, or y equals mx plus b, right? We can graph that linear equation. has a y-intercept of 2. Now there's a couple different ways we can graph this. So I'm going to talk about it if I were to think of it in this terms. Has a y-intercept of 2 with a slope of 1, so up 1 over 1. And we're going to stop here at 4 because they said to look at it on our x-axis from 0 to 4. So if I kind of draw in this shape here, using the idea that the area under our curve, which would be all of this, is going to be our total distance traveled. Well, it's a little trickier than last time because it's not a rectangle. And so I have to recognize what shape we're looking at here. So this time as I look at that shape, I see 2 parallel lines, which makes it the area of a trapezoid. So in case you have forgotten the area of a trapezoid, you will use this a ton. So make sure that you have this down. There's your geometric version of the area of a trapezoid, but I want to take a second to talk about in our picture what that would be. First of all, the bases. So as we talk about base 1 and base 2 in a trapezoid, that refers to the parallel lines. So that would be this segment here and this segment here. Now it's addition, so order doesn't matter. Call one of those base 1 and one of those base 2. And then your height in a trapezoid refers to the distance between your bases. Well, our distance between our bases would be here. So that means we'd have a height of 4. So just looking at this specific example, the total distance traveled will equal the area under that curve, which would be 1/2. Our height or our distance between our bases is 4. Our 2 bases were 2. And then if we look at this one right here, let's talk about this real quick. Maybe I don't know, maybe I didn't draw a good picture. Maybe I don't know what that is, but remember that is at time equals 4. And if I want to know what this point is and this curve is v of t equals t plus 2, I can evaluate it for 4 and figure out where that is. So I'd have 4 plus 2, or at time equals 4, we've got a base length or a height of 6 here, which means our total distance traveled would be, let's see, 1/2 times 4 is 2, times 8 is 16 miles. So what you're going to find out over doing this is this underlying theme is going to be huge for us. Again, the area under the velocity curve is the total distance traveled, which is all great and easy to do if, let's go to our next page, if the velocity is a linear function. And that's the two we've looked at. We looked at a constant, we looked at a linear equation. If it's linear, we would have a rectangle, which we saw. We would have a trapezoid, which we saw. If it happened to have passed through the origin, maybe you would have a triangle. Well, we know the area formula for all of those. And so those are all easy for us to just calculate geometrically. So what if it's not what if it's not linear? Look at the picture we have below. What we'll use is this thing called RAM, or your rectangular approximation method. And so what you're seeing right here is that they're breaking up the area under the curve, because if I take away those rectangles, our area under our curve in these pictures, this right here, let me fill this in with a different color. This is not a shape we know, right? It's got a curved edge here, and then a straight edge here and a straight edge here. That's not a shape we know. That's not some geometric formula I can go do, a rectangle, triangle, trapezoid. And so we have to do this approximation, and what they're doing is they're filling it in with rectangles. So they take the whatever interval we were supposed to be looking at, and it looks like they went from 0 to 3 here, and they broke it into a bunch of different rectangles, and you see it 3 different methods here: LRAM, MRAM, and RRAM. And the L, the M, and the R refer to which part of the base. So if we zoom in on one of these real quick here, let's just look at one of these little rectangles here. Which part of the base we are using to then identify the height of our rectangle. If it says LRAM, it says use the left end point of the base, which would be right here. Follow that left end point up to the curve, and then that's where you draw in the matching base to create the rectangle. And you'll notice that each of the left hand, so if we look at this base right here, it's left hand if I follow it up to the curve. and then I draw the matching base to below is how we create those rectangles. On the one next to it, the M stands for midpoint. And so that's saying use the midpoint of the base. So if I were to, again, look at one of these little rectangles, here's the base. If I identify where its midpoint is and then follow that up to the curve, when it hits the curve, I draw in the matching base to what we had below and connect those. That's where we're getting these rectangles. And then finally, R represents, to use the right-hand side of the base. And so of that little interval that we have down here, I'll use the right-hand side, follow it up to my curve, draw the matching base from below, and then connect those, and we get the rectangle that we'll use to approximate. Now, you see that it is exactly just that. It's an approximation. These are not exactly the area. On this first one right here, we clearly have some spaces that are not accounted for as if we were to add up the areas of those triangles. And in both our midpoint RAM, you have areas above that are extra, areas below that are not accounted for. That's actually going to be a decent approximation. And in our R RAM, we've got all of these little all of these little spaces above our curve that would be more than what the area is. And that's why these are approximations. And so we're going to look at how we can make this better and better approximations as we go, but utilizing this to just estimate the area under the curve. It will not give us an exact area under the curve, obviously, as we have either space missing or space added as we do this. So very quickly, what we're going to do is look at, okay, just drawing these for ourselves. I want to know what the total distance is covered by this, which means I want the area under this curve drawn. And since it's a curve, not a linear equation, we're going to have to approximate it using RAM, a rectangular approximation method. Now, to just kind of ease us into this idea, we're going to draw 4 rectangles to represent the area under the curve. And so what you'll notice is our curve goes from here to here. And if I follow that curve down to my x-axis, it would match up right here, which means along our x-axis, we're going from the origin to that spot. And it said to you draw 4 rectangles. So you'll notice along the x-axis, I've got that broken up. And if it wasn't already broken up for me, I would break it up. There's midway. So then break each of those in half. And I have 1, 2, 3, 4 little equally spaced bases along there. And then using our right RAM. So what I'm going to do is I'm going to take one of those little bases. Let me zoom in on this just a little bit here. Take one of those little bases. So starting here at our origin, going to that first spot would be my first base. And it said to use right RAM, which means of that base, I'm going to use the right side of it and connect the right side of it up to my curve, because it said R RAM. And so once I hit that curve, this base that I had drawn here, I draw that same base up here and then finish connecting those 2 bases. And there's my first rectangle. And we keep doing that all the way across. So then again, here's my base. Its right-hand side would be here. Follow that right-hand side up to my curve. When it hits my curve, that same base I had below, I draw above, and then I connect them back together. And then I do that again. Here's my base. There's a right-hand side connected up to my curve. And we've got our base below, base above, connect, back. And finally, our base here, I kind of already have it connected up to the top. Draw in that same base, connect back to the bottom here. And so then if I wanted to estimate the area of the curve, what I can do is take the base and the height of each of these little rectangles and add them together. And that gives me an estimate for the area under that curve. And this one clearly, visually, is an overestimate because of these little spaces that all fall above my curve would give us an overestimate. And some of you may be thinking at this moment, like, why would we use right RAM or left RAM when midpoint RAM seem to be the obvious better choice? Well, these are a very basic curve, not always the best option sometimes. And maybe we want an overestimate or maybe we want an underestimate. So it kind of depends on our situation and our curve. So let's go ahead and do that for each of the others here. Left point RAM, again, if my curve is going to start here and end here, I would connect the end of my curve, or wherever we were supposed to do this to my x-axis, break it into 4 sections because they told me to draw 4 rectangles. I'm going to use the left end of each base to connect it up to my curve. So as I start with that first base, I now use the left-hand side to connect up to my curve. And that base that I have drawn here at the bottom, I repeat that at the top and then connect back to my base. And notice this one ends up being an underestimate because we've got some space between the top of our rectangle and our curve not accounted for at the moment. But again, here's my next base. Use the left-hand side to connect up to my curve. If you didn't print the note sheets, you can just draw a basic curve yourself to practice this. I know that seems like it would be an easy thing to do, but you would definitely want to practice this with at least one time here to draw these. Here's where it hits my curve, connect back, and my final one, again, using my left hand approximation where it hits my curve and connect back, and that would clearly be an underestimate. So last one we want to see being able to draw by hand would be our midpoint RAM. And again, that's using the midpoint of our bases. So as I get this one set up, my base would be, so again, same interval. My first base would be here. And this time I'm going to use my midpoint. So I'm going to approximate where that midpoint is and connect that up to my curve, which would be here. And so that base that I had down here, I'm going to repeat that through where the midpoint hit my curve and connect the sides back down, giving me that rectangle. So let's do that again. Here's my base. Its midpoint is approximately here. We connect the midpoint, and through the midpoint's intersection with the curve, I draw that same base I had below and connect it back. And again, kind of looks like this would be our best because this is a nice curve for this to happen. Use my midpoint. And our last one here of 4 rectangles. It's not always 4 rectangles. That just happens to be what this particular question asked us to do. So you would break it into whatever number of intervals they tell you and use whatever side of the rectangle they tell you to draw. All right, so if you have questions on that, let me know. But that is your RAM approximation method when we don't have a linear velocity to be able to find the area under. Now, obviously, this can be improved upon. So we're going to kind of continue to look at how can we improve upon this to get the best estimate for the area under that curve so that I can start eliminating things like these over and under spaces that are happening here so I get an even better estimate. So what we're going to do is look at a specific curve here, and I'm going to walk you through step by step, and we're going to go look at this Desmos calculator here at the end, but don't jump ahead of me. Stay with me at the parts A and parts B here. Part A says graph the region defined by f of x equals 4x minus x squared and the x-axis from 0 to 4. So let's start with part A. I'm going to do my part A up here. And I'm going to pretend I don't have a calculator here. I'm supposed to be graphing this from 0 to 4. So 0, 1, 2, 3, 4. Okay. Now, how am I supposed to know what this graph looks like? Well, I mean, I could go to my calculator, but guys, I can also evaluate, right? If I want to know where this is supposed to be, can't I just do f of 0? Well, 0 minus 0 is 0. So f of 0, that would be the 0.00. And I can keep doing that for each of those points, right? And just give me 4 points to kind of connect. Now, I know this is an upside down parabola by what I know about my functions here. Plug in a 1. Let's see, 4 times 1 is 4. Minus 1 squared would be 3. So I'd have a point at 1, 3. And do that same thing for 2. If I plug 2 in there, 4 times 2 is 8. Minus 2 squared is 4. So 8 minus 4 is 4. Plug in a 3. 4 times 3 is 12. Minus 9 would be 3. and plug in 4 would be 16 minus 16 is 0. And you can see that parabola happening here. And that would be our curve graphed from 0 to 4, part A. Part B says to partition that into 4 sub-intervals. Well, that kind of works out nicely since it goes from 0 to 4. Here's my 4 sub-intervals. 1, 2, 3. Let me do a different color here so you can actually see that. 1, 2, 3, 4. There's my 4 subintervals. And it says use right RAM to approximate that area. Now, I don't actually have to draw the picture, but I'm going to this time to kind of help us. So as I draw each of these rectangles, there's my base. Use the right-hand side, which means it's going to connect up to this dot right here. And that rectangle, if I think about using it to approximate the area, would have a base of 1 and a height of the right-hand side, f of 1 was 3, and keep going. So then if I do my next one here, there's my base of 1, height, I'm using the right-hand side, which connects right here. Base of 1, height of f of 2, which was 4. And keep going. So my next base would be here. Again, base of 1, height of f of 3, which was 3. And our last one. Okay, let's look at this last one real quick. So here's my base. I'm supposed to use this dot to connect to my curve, but isn't that dot already connected to my curve? And so this can be a little bit weird, but that rectangle is already drawn. It has a height of 0. So I mean, I can write that in here, base of 1, height of 0. It's not going to change. It doesn't add any area as we're approximating the area into the curve. Again, kind of one of the downfalls to this approximation method here. So then putting all that together, let's see, that'd be 3 plus 4 plus 3. I would estimate the area at 10. And it kind of looks like, I mean, we got some area above, some area below. So I'm not really sure if this is a great over or underestimate. We kind of have some overestimate and some underestimate. We'll see. So now what I want to do is go to the part C. Now, in years previous, I would have put a program on your calculator, which would have taken us a long time and is actually kind of pointless because you don't use this very often. In fact, you don't really use this ever once we kind of move past learning about this. And so what we're going to do is utilize that Desmos calculator that I put on Google Classroom for you. You will continue to have access to the Desmos calculator, and I want to show that to you now. So let's go ahead and flip over to my Desmos calculator here. And in this one, what it allows you to do is in this very first line that you see when you go to this Desmos RAM calculator is it allows you to type in whatever function you want. So let me show you here with the function we were doing. We did 4x minus x squared. Now, right now it looks a little bit weird, but you'll have to pay attention. Right here it says +1 and then a is less than x is less than b. That's moving the graph up 1. It's just how this person created this one. I don't want to move the graph up 1, so I'm going to put a 0 there. But then also a and b refer to the interval at which we want to look at this on. And so we wanted to look at this from 0 to 4. So I would change our a and b from 0 to 4. Okay, and so now I have this drawn from 0 to 4, and there's my picture. So here are your options. N refers to our number of rectangles. We initially did 4 rectangles, and we did them with using the right endpoint, and that's what's highlighted here. I could, instead of doing the right endpoint, I could do the left endpoint. Notice this first rectangle doesn't show up because its left endpoint is already on the curve. Instead of doing left endpoint, I could do midpoint. Okay, but we did right. So that's what ours matches. Now, on part C of the question, I asked you to do this using the RAM calculator and to do this same picture, but instead of 4 rectangles, I want you to do 10 rectangles. And what you'll see here is if we use the right end rectangle formula here, if I scroll down a little bit, it says right endpoint approximation. It's totaled up those 10 rectangles for me instead of me having to do it by hand. And it told me that it was 10.56. And so with n equals 10, we get an area of 10.56. And I'm going to go back up here and change it because then I asked you to do this for 50 rectangles. And notice as I draw in 50 rectangles, they really start matching my curve a lot better than like when I had, let's say, 5 rectangles. That doesn't even hardly match my curve. I make it 50 rectangles and it starts to appear more like the shape of my curve. So now let's go see what they say that if I added up the area of each of those 50 rectangles down here at the right end approximation, it now says that it is 10.6624. I'm writing this down in our notes so that when we go back to that, we can find it. Okay, then the next thing I asked you to do was for 100. And you can see even more, it's starting to look even more like our curve here. And as we scroll down, they added up all 100 of those little areas and got 10.6656. And so what I'm basically showing you, and it's a nice visual for you to be able to see, is that the more rectangles we have, the better the approximation. Now on your calculator, when I ask you to do this very last one, is that it would have taken forever to actually type, to actually show up. And it kind of looks like it really just like fills in the picture here. But if you zoom in, which I'm not sure if my computer will let me do here, but if I were to zoom in, let me see if it'll zoom in. Nope. There we go. You can see that there are little rectangles drawn in there, 500 of them from 0 to 4. And as we, scroll down here then for our approximation, you can see that it's getting closer and closer to, looks like 10.6 repeating, which would be approximately 10 2/3. And so that's telling me that the area is really, really close to, if not exactly, 10 2/3. So in your assignment, you are welcome to utilize that Desmos calculator on the appropriate problems. And you can see the more rectangles we have, the more exact those numbers get. Okay, moving on. The last thing that I want to look at for you guys today is doing the same idea, but from a table of values. And so one of the things you can do with your table of values, especially as you're getting used to this, because actually this format, this table of values, and asking you to do an approximation is going to be the more common way that you will see this concept show up than you will like drawing in rectangles and approximating it. It'll be from a table of values like this. The more we use it, the more we will get efficient at this. But to start with, on this very first time we're getting introduced to this, what we could do is just graph ourselves a picture of what is happening in this table of values. So in this table of values, first of all, it says we've got the velocity of a model train for 10 seconds. Estimate the distance traveled by the engine using 10 subintervals of length 1, using right ram and left ram. And then at the bottom, I actually added another one that says using MRAM and 5 subintervals. Okay, so let me zoom in on this just a little bit here. So as we do this, first of all, and again, this very first time that we're doing this, what we might want to do is just kind of give ourselves a visual of what's happening with these table of data. So if I were to kind of repeat what we did earlier, I would put my velocity here, which would be my inches per second. And I kind of scanned through those values. It looks like we get up to about 22. So if I go maybe like 5, 10, 15, 20, 25 here. And then we go to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And again, this is not something you're going to need to do eventually, but it'll just help us on this very first time of going through this, visualize what's happening. And so these are just like ordered pairs. So you see like the 0, 0. Well, 0, 0 would be an ordered pair at 0, 0. And then we've got 1, 12. So I can put a dot at 1, approximately 12. 2, 22. 3, 10. 4, 5, 5, comma 13, 6, 11, 7, 6, 8, 2, 9, 6, and 10, 10. And I can connect that so you can kind of see this continuous velocity curve that we have going. And we're going to approximate the area under that using whatever's asked of us. So when it says use the right RAM, now it says estimate the distance traveled of the engine using 10 subintervals of length 1. Well, we went from 0 to 10, which means each of our little rectangles that we are going to draw will be a base from connecting one number to the next, from 0 to 1, 1 to 2, 2 to 3. Those would be each of our bases. Our bases are going to have a length of 1. The height will depend on the question. So the first question is our right RAM. So as we look at that first rectangle that is going from 0 to 1, we will use the right number, which would be 1, to find our height. Well, the height at 1 was 12. I can draw that rectangle, but I don't really want to draw in all these rectangles, but you can see that our height would be 12. So our base from connecting 0 to 1 would be 1. Our height would be 12. And as we do that again for our next rectangle here, which again, we go from 1 to 2, from 1 to 2, we're going to use the right-hand side. Well, the right-hand side is going to be 2, so the height of that one would be up at 22. And there's our second rectangle. Base of 1, height of 22. And what you'll notice as we do each of these is as I connect these numbers, you use the second number's height for the height of that particular rectangle. All of the bases will be a length of 1, which we're going to come back to. So from 3 to 4, we'd use a height of 5. From 4 to 5, we'd use the height of 13. Right-hand side, from 5 to 6, we'll use the height of 11. From 6 to 7, height of 6. 7 to 8, height of 2. 8 to 9, height of 6. And from 9 to 10, which would be this last little rectangle right here, the right-hand height would be up at 10. Okay, now here's a little bit of practical advice from you as you guys might be grabbing your calculators to type this in. If they give you equal subintervals, all of our subintervals are equal with a length of 1 or a base of 1. Notice they all have a 1 here. That's a GCF. So as I type this in my calculator, I would pull that GCF out front. So actually this is what I'm typing in my calculator. I know 1's not going to change anything. Let's pretend the base was 5. I'd put a 5 out front, whatever that common base was. And then I can just add up all of the heights. And just save myself a little bit of typing there. Okay, any questions, let me know. But then we repeat that process for our LRAM. So this time around, as we connect those bases, I would be using the left-hand side of my rectangle instead of the right-hand side. So for example, as we connect that first one, let's go from 0 to 1. The left-hand number would be 0, so I would use the left number for each of my heights. So our first rectangle from 0 to 1 has a base of 1 and a height of 0. My second one from 1 to 2 would have a height of 12. Again, using the left-hand number for each of these. From 3 to 4, left-hand height would be 10. From 4 to 5, our left-hand height would be 5. From 5 to 6, our left-hand height would be 13. From 6 to 7, our left-hand height would be 11. From 7 to 8, our left-hand height would be 6. And from 8 to 9, it'd be 2, and from 9 to 10. So that's this last rectangle again. Now the last rectangle, the left-hand height is 9, and it would look like this with a height of 6. So again, we could type all that on our calculator, and I grabbed mine so we can go back and put some values here. The one we just did, if you were to type all that in, ends up with an answer of 87 inches total distance traveled. And the one above, if I go back and type all that in, ended up having 97 inches. So you can see we've got a overestimate, underestimate. Okay, so let's look at the last one, that midpoint RAM. Get rid of my marks here. So as we look at now that picture that went from, let me draw a picture down here. That went from 0 to 10, and we kind of had this curve going on here. Now I'm supposed to split it into 5 equal subintervals. So to split that into 5, if I take 10 divided by 5, it means the base of each of these is going to be 2. There's my 5 subintervals. So now as I draw my rectangles, the base will be 2, and I'm supposed to use MRAM. Okay, well, let's look at that. The midpoint from 0 to 2 would be 1. And so the height I would use for my rectangle would actually be the value as I connect from 0 to 2, the height of that rectangle will come from the midpoint between those two. So our height would be 12. So my first rectangle has a base of 2 and a height of 12, and we can keep doing that. So my next rectangle that goes from 2 to 4, its midpoint is at 3. Again, base length of 2 from 2 to 4. Height, using that midpoint value, at 10. Next rectangle goes from 4 to 6. Its midpoint is at 5. So a base of 2, height of 13. Next one goes from 6 to 8. Height would be using the height of 7. So 2 and height of 6. And your last rectangle is going to go from 8 to 10. So base of 2, height of, use the midpoint, 6. And using 5 subintervals and a midpoint RAM, we end up with an area of 94 inches, or a distance traveled of 94 inches. Again, connecting the area under the velocity curve will give us our total distance. All right. We do have a few minutes left, so I'm going to leave some time for questions here, but let me move to our assignment. First of all, your assignment is out of the book, and I don't know if you guys saw my message. I just got a call this morning from one of the other calculus teachers that just today they removed access to our online book, and so we have the PDF version. I have posted that in your Chapter 6 materials, so you'll have to go to that to get your online book access now. And you're doing page 274, 1 through 6. On 1 through 6, that's like your geometric, use your algebra, not the computer program that I just gave you. I know it says calculator, computer program. Do not use that. Use your geometry. And then 9 through 12, 17, 19, 23, 24, and